Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so finding bugs. So there are lots of different ways to find bugs in programs. One of the ways is to use static analysis for defect detection. So static analysis is something that looks at your program and thinks about it real hard without actually executing your program. Generally, static analysis doesn't depend on having good test cases or any test cases. Generally, for the type of static analysis I'm talking about, it doesn't know what your software is supposed to do. Therefore, it can't actually check that your software does what it's supposed to do. Rather, it has rules of thumb about what shouldn't software do. So software shouldn't dereference a null pointer. Software shouldn't access an array outside of its bounds. It shouldn't allow for SQL injection, which is taking untrusted input and using that to form a SQL query. This is not a replacement for testing. It's very good at finding problems on untested paths, but there are lots of defects that you just can't find with static analysis. Now, when I started work on this problem about 4 or 5 years ago, there seemed to be some common wisdom about bugs in static analysis, both in the developer community and in the research community. So, well, programmers are smart. Smart people don't make dumb mistakes. We have all these good techniques for unit testing, pair programming, code inspections to find bugs early. So if there actually are bugs in production code, well, those bugs have to be subtle, and finding them must require sophisticated static analysis techniques. And people do very elaborate, context-sensitive pointer alias analysis scheme to allow them to find, oh, we can, if we do this, then we could find some very subtle bugs. Because if you use something simple, well, we tried lint, and well, a lot of people think lint kind of sucks, right? Okay, so here's a bug. This is actually a bug that was in Sun's shipping version of Java 1.6. Okay, and can you find the bug in this? Right. So, I'll stop the music. Okay, so if listeners is equal to null, then invoke a virtual method on listeners, right? So this code, it actually manifests itself in 2 different ways. If listeners is ever null, we'll get a null pointer exception. But actually, perhaps the worst problem is that if listeners is non-null, we won't ever remove anything from it. Okay, and you don't need a context-sensitive pointer alias analysis scheme to find this type of error. Right? So why do these bugs occur? Why do they make it in production code? Nobody's perfect. There are lots of common types of errors: misunderstood language features, API methods, typos. We see a lot of that. People just use the wrong Boolean operator. They forget parentheses or braces, or they put in an extra set of parentheses. Misunderstood class and method invariants. So everybody makes syntax errors, and you sort of depend upon your IDE or compiler to catch them. And the question is what about a typo that's, results in another semantically valid program, but one that's still things? So now, rather than starting with analysis techniques and figure out, well, what can we use, what can we find with these, the way we've sort of looked at it is coming up with a bug pattern. A bug pattern is, well, what's a type of mistake that people make? And there are all sorts of different ones. So dereferencing a null pointer is a type of mistake. An impossible checked cast. So if you try, you find something and you say, oh, I'm going to take this and cast it to be of type string. And if you can detect through type inference that the thing you're casting is guaranteed not to be a string, well, that's an error. Right? Methods whose return value should not be ignored. I'll be talking about that in an example. And one of the things that we've been doing in FindBugs, and this is perhaps one of the things that we do perhaps a lot of, is we look at lots of little small programming mistakes. So there's something that's been done, Joshua Block and Neil Gafter have done this at Java 1 for a number of years, called programming puzzlers. They have a talk called Programming Puzzlers, where they give people a code fragment and they ask people to figure out what this code does, and it typically befuddles more than half of the audience, all of whom are experienced developers, because it depends upon some quirk of the Java language that is easy to get tripped up on. Joshua Block has a book called Effective Java, which talks about good programming practice. One of the things we did is we went through that book and said, okay, every single rule it gives, is that something where we could find violations of that using static analysis in a way that would be useful? There's a great little website called the dailywtf.com where people post horrible code that they found in production settings. And we scan through those, and we sometimes find some interesting mistakes. Okay, so those are some of the types of things we look for. What do we use to find these? And the key thing is we use the simplest thing that works. So in Java, strings are immutable. And so there's a method called toLowerCase that when you invoke it on a string object, it returns a new string in which all the characters have been converted to lowercase. And so if you ever see a statement like s.toLowerCase, paren, semicolon, and just the function call with the return value being ignored, that's valid Java, but it's almost certainly wrong. It probably means that somebody, wrote that as though they wanted s to be replaced with a string in which everything had been converted to lowercase. And you don't need fancy analysis to figure that out. You just see, oh, here's a method call, it returns a value. This is one of these methods whose return value shouldn't be ignored, and yet you're ignoring it. We do sometimes in order to find it, that's not enough. You can't do simple pattern matching. You have to do intra-procedural data flow analysis. So we get a lot of our null pointer typecast errors that way. So in FindBugs, we use interprocedural method summaries for, we find a method that always dereferences its parameter. That's been useful in terms of helping us find more mistakes. One of the things that we don't do, but other people do, is context-sensitive interprocedural analysis. In particular, if you want to find interprocedural use of untrusted data for things like SQL injection, cross-site scripting, you really need to do more sophisticated interprocedural analysis. Yes?
So what's the definition of ignoring the return value?
Okay, so in this case, well, the definition of ignoring it are sort of what we detect, right? So if we just see that you have a method call, and our system knows a list of methods whose return value should not be ignored, right? Now, if we see a call to that, and you don't do anything with the return value, right? You don't assign it to a local variable, you don't do anything with it, then we flag it.
But then I can also assign it to a temporary local variable and not do anything.
Yes, exactly. And that keys in to one of the things. There's an advantage to using simple techniques, and there are a couple of advantages. One of them is that when you use a simple technique, it becomes much easier for a developer typically to understand and fix the issue. Right? The other thing is okay, we have two cases. One where you have a string variable and you just say s.toLowerCase, and you do nothing with it. In that case, it's pretty clear from the context that the developer simply misunderstood how that method works. They thought that the method changed the object, but it didn't. Whereas if they did the computation and put the result into a local variable, and then they later didn't ever use that, that is semantically equivalent. But that's probably indicative of like leftover debugging code or something like that. It's just it's a dead local store. We detect that. It's actually a separate issue. But it actually reflects a different type of mistake, right? The user understood that this method returned a value. He just didn't bother to do anything with the value, right? And so if we actually use data flow to figure out, well, is the value of this method used, right? I think perhaps, here's a different way of saying it. What we really know is that not so much that the return value of this method shouldn't be ignored, but rather, if you invoke this method, you should demonstrate that you understand that this method returns a value, right? As opposed to being a method with a void return type. Okay, other comments, questions? Okay, now one of the things that we do in FindBugs, this is a lot of things other stakeholders, and actually, I would love to have more experience with prefix, prefast, fxcop. I don't, so I'll tell you my experience, and I'd like to hear more about others. The tools we use and so forth, different bugs get classified into different categories. We have rules and patterns about what find bugs. We rate things with different priorities. We think this is the highest priority issues. We think these are less priorities. Some issues just relate to performance. This is maybe something which is not the most efficient way to do things, but if it's in code that's only executed on startup and so forth, well, maybe it's not so important. Where if it's in your critical inner loop that's very performance critical, you care a lot about those. One of the things that we find talking to people is that there are a lot of different use cases for static analysis. Sometimes you've got some newly written code, 1,000 lines of newly written code, and before it gets checked in, you want to do a review of it. In that case, you might be interested in lots of sort of advice that your tool is giving you about your code. I mean, this code hasn't really been tested, it's not been in production. You're doing a code review, and maybe a tool that gives you a lot of warnings about that 1,000 lines of code is, 10 warnings about 1,000 lines of code. Yeah, that's fine. But on the other hand, if you want to scan 1,000,000 lines of code that's been in production for a year, you don't want 10,000 warnings. You can't cope with 10,000 warnings. Your developers have better things to do. And so one of the things in FindBugs and other things is we have to figure out, okay, you are scanning a large legacy code base. Well, you want to be looking at only these sorts of issues. You don't even want to bother looking at low priority issues and so forth. Whereas we have other people that when they're doing it on new code greenfields, they want to do things different. So different use cases require different issues. So we have one category called correctness, where it's the issues we're most confident that the code is wrong. Right? The code does something the developer doesn't intend. Many of the other issues actually reflect places where the code is wrong, but if you're looking at a 1,000,000-line code base, we put that in that category. So low false positive rate, few low impact bugs. Okay, so how do we go about finding bugs? Well, I'm at a university, and it turns out that students are really good bug generators. Right? So a student came to office hours, and he was having trouble with the constructor for his web spider class. Right? So in the constructor for web spider, he said web spider w equals new web spider. Right? Well, that will create a new object of type web spider, then invoke the constructor to initialize it. Right? So this is an infinite recursive loop. Right? It'll just successfully create more and more objects until you run out of stack. And this was a freshman course, I hadn't talked about what's a stack overflow. I hadn't even talked about what a stack is. Right? A second student came in with the same bug. Right? And at this point I realized that really it was my mistake, because I'd given them this method template. I said, fill in the body of this method, and I'd given them a comment, construct a web spider. Right? And so that's what the students proceeded to do. I should have made the comment, initialize a web spider. Right? And so I wrote a detector for FindBugs to find this, and we actually do some stuff where we actually do lots of interesting stuff, if anybody wants to talk to me later, about how we use static analysis and unit testing in our curriculum, and the students get a lot of exposure to unit testing and write their own test cases and so forth. But anyway, so I wrote a detector, was able to look at, while the students were still working on the project, was able to look at other ones, found other students who had the same bug, said, okay, yeah, I'm finding real bugs here. Let me add this to FindBugs. But before I add it to FindBugs, well, I should check to make sure that I'm not generating lots of false positives, because people don't like false positives. Tell you what, let me run it against Sun's JDK, because, well, Sun's JDK shouldn't contain any infinite recursive loops. And when I ran it against Sun's JDK, I found 5 infinite recursive loops in Sun's JDK. One of them was written by Joshua Block, who is one of the people who had been one of the lead developers of the software libraries at Java at Sun, wrote most of the java.util classes, and he had written a one-line method that returns the result of invoking itself. And the reason he wrote that is this was supposed to be a getter method. There was a field called foundType. And so the mistake was just having the set of parentheses. Right? Without the set of parentheses, this getter method would have returned the field. Right? And this opens up a whole question as to whether or not getter method should be named get whatever, but at any rate. So I've got a t-shirt, one of my FindBugs t-shirts has this code on the back of it with Josh's name. Josh also has one of these shirts with his code, with his name on it, and he wears it at Google. Right? And one of the lessons I take from this and I tell people is that smart people make dumb mistakes. Google has removed more than 80 infinite recursive loops from their code base. Over all versions of the JDK, they've removed 27 infinite recursive loops. And so one of the things when you start using tools like this is that it turns out everybody makes stupid mistakes. And you just got to get over the ego issue with like, oh, I don't like these tools. Everybody makes them. Yeah?
Do you think that mistakes can be slightly less dumb as being shown here? For example, I'm returning some other function which is returning this .found type, which would require something a little bit more than a local analysis.
Right. So we actually do some stuff, getting back to student code, where we actually can take all the student code that was submitted over a semester, and we can look and run through all the unit tests, and not only just the final code, but actually all the intermediate codes. And one of the things we can actually do is find, well, what are all the cases where there was a stack overflow, right? And then we can look and say, okay, of the places where there was a stack overflow, how many cases were we able to report a using static analysis in infinite recursive loop? And there were a number of cases where there was mutual recursion or something like that, and we just make no attempt to report it. By looking at it, we did find a number of cases that weren't found by our current detector, and we were able to improve our analysis to report them. But we're not trying to do static analysis that will guarantee your code has no infinite recursive loops. We are trying to, it's actually very much limited by manpower. What is the most effective way for us to spend manpower implementing new static analysis? How do we implement analysis that gives the reports that are going to be most effective for developers to look at? Because when you start worrying about, well, here's a potential infinite mutual recursion that could be infinite, well, is the false positive rate going to go up? And so we're not trying to prove safety properties. I mean, that's another thing you can do with static analysis. You can try to use static analysis to prove that you never dereference a null pointer. And that's a great thing. It's hard to do. And when you try to do it, typically developers have to deal with a lot more warnings, and they have to put in a lot more annotations and so forth. And it's a great thing. It's not what we're trying to do. We're trying to use the minimal amount of work to come up with the most likely errors. Okay. So we're talking about null pointer bugs. Right? So you can do very complicated things with null pointer dereference finding. And typically for languages like C and C++, you do. It turns out in Java, dereferencing a null pointer isn't that bad, right? Because it just causes a runtime exception. And it's not as bad as causing a seg fault, right? And so once again, we're not trying to prove that you never dereference it. We're just trying to find the obvious ones. And one of the problems you get into with static analysis is, well, here's a path on which you can dereference a null pointer, but is that path feasible? Right? And that can become a very hard problem. So we don't try to solve the very hard problems. Instead, we look for a statement or branch that, if executed, guarantees a null pointer exception. And we actually have made a couple of iterations to getting more and more cases, but still under this. So we never actually try to tackle the infeasible path problem. Well, we just try to find a statement or branch that, if executed, guarantees a null pointer exception. And so this means either the null pointer exception could be thrown, or the program contains a statement or branch that can't be executed. Right? It is often the second one. When we find this, it's often the case that, oh, well, yeah, this is a bug, and the bug is that we're never supposed to go down this path. You could look for exceptions that occur only on a path. Just if the condition on line 29 is true and the condition on line 38 is false, then a null pointer exception will be thrown. But then you got to worry about whether or not the path is feasible. Yeah?
Why is the seg fault worse than a null pointer exception?
Because typically in, opinions vary, right? Typically in a desktop application, if you're like processing a menu option, what will happen is that the attempt to process that menu option will fail, and you can have some sort of high-level thing pop up in memory, but the whole memory state is still valid, and the application can continue executing. Well, it can't be arbitrarily corrupted, right? You can have a transaction that's half done, right?
You're saying that in a C program you don't have that exception handling mechanism.
Right. Yeah, I mean, you got to segfault on the whole things. Turns out, so for example, at Google, for their web applications, they don't care that much about null pointer exceptions, because if a null pointer exception was happening with any regularity, they would see it in server logs. They have traces that generate this stuff. At Google, they're much more concerned about a computation that will silently produce the wrong answer, because that might be silently producing the wrong answer millions of times a day. Whereas a null pointer exception that happens under some weird condition, okay, yeah, maybe that's there, but it's not, so it aborts a query. If it aborts one query a day, it's not a big issue, or at least not as important as other things that developers can do. And this is all an issue. It's not to say this isn't potentially a bug, but it's what's the relative importance of it.
So segfault has the same property, right? It's not going to...
Well, it's not going to corrupt the system, but the app disappears. And actually, one of the things which is interesting, so on an iPhone, one of the things which is interesting is how cosmetically beautiful they've made segfaults, right? When your application segfaults on an iPhone, it just disappears back to the home screen. You think, oh, maybe I accidentally hit the home key, right? So that's one of the things Windows should do, is they should make segfaults more cosmetically beautiful. So this is what we found in Sun's released version of Java 1.6, 109 statements or branches that, if executed, guarantee a null pointer exception. Now, we went through those trying to hand categorize them. Now, this is human judgment. And we found 54 of them that we deemed to be bugs that could actually dereference a null pointer on valid input. Most of the others were deemed to be unreachable branches or statements, or you have a method that, well, if you pass it a null argument, it tries to handle null inconsistently and will wind up dereferencing it. But when you look at it a little bit more, you say, well, but nobody's ever going to pass null to this method. It doesn't make sense to pass null to this method. Only one case where the analysis was actually wrong. Here are a couple of examples of the things we can find with very simple analysis. So we're checking for name not equal being null, name.length being greater than 0, and then when we're doing something and people say, well, good, we're checking for both those things, but when you actually look at it, well, what happens if name is null? Well, if name is null, then the first branch is false, and since this is an OR, we're only going to evaluate the right-hand side when name is null. So name.length will only get evaluated under the situation that name is null. Here's a place, part equals null, part dot equals quote. So if name is null, the left-hand side is true. So we shouldn't have to evaluate the right-hand side. But because there's only a single vertical bar, we always evaluate the right-hand side. Here's a place where somebody put in a check to make sure that we don't call paint scroll bars if G is null. But then one line down, we dereference G. Right? And once again, this might be a case where somebody was writing this code and says, oh, I don't know whether or not G is allowed to be null here. Let me put in a defensive check. And down here, there's no defensive check. And maybe it turns out in this context that G simply never is null. It doesn't make sense for G to be null. Yeah, question?
How many patterns do you think we have to write? Won't the list keep growing as we have more programmers with innovative coding styles?
The list, hopefully the list will keep on growing, right? I just added one on yesterday, and I'm going to talk about it. The thing is that we find a number of bug patterns that, okay, this, somebody came up with this. It took me 4 hours worth of work to implement it, and it finds about one real bug per million lines of code. Okay, and I add new bug patterns like that, a couple a month, right? And it's not a whole lot of work to do, and I keep on finding more bugs. The bug patterns, null pointer dereferences, there are lots of bugs like that. And the question is, how many bug patterns are there that find lots of them? I'm not sure how many. You maybe think about more. But yeah, one of the things is there is no one set of, okay, here's all the types of mistakes you make. You have to keep on thinking about what are the sorts of mistakes people make. Your question, yeah?
You said that for this case, you don't look at, try to figure out whether paths are feasible or not.
Right.
But, I mean, it's a very short path, but it's still a
Ah,
path. So you must
but-
have some
right,
idea of
so-
some window that you are willing to.
Now what I'm looking for is a branch or statement that, if executed, guarantees a null pointer exception. If I take the else branch from this if statement, I'm guaranteed to get a null pointer exception. Right? Right. And basically the idea was what was the point of...
Path, that's on the,
Well, it's simply an edge.
The branch is not taken. It's just, but this statement could have been further down. Right? I mean, there could be paths in between.
There could be paths in between, in which case, so if there was if foo called g.dispose, we would not report this.
Okay, so you look at the statement immediately as the branch target.
It's not just immediately. So we actually do something where we'll see, like, if g equals null, and we do a branch here, and then if we turn here, and we go down, and if we branch again, if I just dereference g on one side, I won't report it. But if I dereference g on both, I will. Right, so if I dereference g, if I dereference it on both, I'll do it. And actually the technique we use for this is we do a backwards propagation of what values are guaranteed to be dereferenced on all non-exception paths. Right? And when a backwards propagation of which values are guaranteed to be dereferenced collides with, I know on this edge this value is null, we report an error.
I think so, but your middle example doesn't follow that rule.
Actually, it does in sort of a complicated way, because this computation actually involves where we have a branch where we're turning the true or falseness of this into a 0 or 1. And then after that, we always dereference it. So another type of null pointer thing to look for is checking to see if a value is null where it can't possibly be null. Right? So here's a place where we pass in a couple parameters, we get the number of bands from the destination raster stored in the destination length, and here we check to see if destination is equal to null. Right? Can't possibly be null because we've already dereferenced it. Right? And so we're going to report this as a warning. Right? Is this a real bug or not? Right? And well, there are two possible things that are going on here. Either you should never pass null for this parameter, in which case this check is redundant, right? And we see that. Or maybe you are supposed to be allowed to pass null for this parameter. In this case, we can check the documentation for the method, and it tells us that if the destination raster is null, a new raster should be created. So the documentation clearly says that this method should handle a null parameter, and we're not doing that. Okay, so that's what we do for null pointer detection. Okay. So bad method invocation. So we have these methods who, like I said, return values shouldn't be ignored. Perhaps that's not really the right way. It's really methods that if you invoke them, you need to show that you know this method returns a value. Right? Turns out that there are a bunch of dumb and useless methods. So in Java, everything is an object. Arrays are object. But if you invoke the toString method on something that's an array, you don't get something which is a useful representation of the contents of that array. You get like, a bracket and some other symbol telling you what the type is, and then the hexadecimal address of the array or the hash code of it, or something like that. And that's not useful, right? Generally, if you see that, that means somebody meant to do something like convert it into a string representation. If you compare two arrays using the dot equals operator, that's not too useful because dot equals on arrays just tells you object identity. Right? If you actually want to check the contents of the array, you need to use a different method. And so it turns out that there are lots of specific rules about particular API methods. These are hard to memorize, easy to get wrong. So some examples of a bad method. So this was from some SQL code. In this case, we're going to call the setScale method. And actually that method looks just fine, except it turns out that setScale is a horribly named method. Big decimal is an immutable object. You cannot change a big decimal object. The setScale method actually returns a new big decimal object whose scale has been changed. Right? Here's a place where we try something and we catch an exception, and in this case, if an I/O exception, we should be throwing a SAX exception rather than an I/O exception. The problem is we create an exception, but we don't throw it. Right? And so what happens is that the I/O exception gets caught, we create a SAX exception, and then that exception is dropped on the floor, and we proceed normally not having thrown any exception. Right? And like that one comes up fairly regularly. You know, basically it's a rule that if you create an exception object and don't do something with it, that's probably a mistake. So we do type analysis. We try to figure out what the types of objects are. We look for a check cast, which is impossible. Sometimes it's like a cut and paste error. You know, we'll actually see code. We make use of instance of checks in our type analysis. And we'll see where somebody says, well, if x is an instance of string, then cast it to a string and do something with it. Else, if x is an instance of string, then cast it to an integer and do something with it. Right? Another thing we do is, so in Java, the equals method takes an object as a parameter. So you can compare any two objects. And if you see code where somebody is comparing a string and a string buffer for equality using the equals method, it's almost certainly wrong, because that's always going to return false. And probably what it means is that they meant to compare the string representations. They want to maybe take the string buffer and convert it to a string before comparing. And you see all sorts of variations. People basically, they're comparing the wrong objects. Right? Somehow they made a coding mistake. They're comparing the wrong objects. We don't know that they're comparing the wrong objects, but we know that they're comparing them of the wrong type. So Java added generics to their utility classes, and so the map operator turns out that if you have a map from, say, strings to integers, right? Well, if you try to add something to the map, it's going to type check that the key value is of type string and that the value object is of type integer. But when you call get on a map, it allows you to pass anything to the get method because it's type safe, right? And there are actually occasions where you might write code that does that. So you might have a map from strings to integers, and maybe you're iterating through a list of objects. And for each object, you're saying, does this map contain this object? And that's valid code. It's type safe. And actually, we're not going to signal an error in that case. But on the other hand, if you have a map from strings to objects and you call get, and what you're passing to get is an integer or a string buffer, then we know that, well, this is type safe, but we should never find anything here. Right? That if you have a map from strings to integers and you pass it string as an argument to get, it ain't there, and that's probably an error. So that's one of the things we find. Okay, so type analysis, this is one of the big patterns. Now I'm going to dig down, show you a few of the small ones. If we see, checking to see if d is equal to double dot not a number. So in the floating point representation, there's this special value called not a number, right? It's what you get if you divide 0 by 0. And if you ever see if d not equal to double dot not a number in code, you know it's wrong, right? Because nothing is equal to not a number, not even not a number, right? Actually, if you want to check to see if d is the special not a number value, the way you check is you ask if d is not equal to d, right? Now that's very confusing because, so there's actually a method said, double dot is not a number that you can use instead of that so that people actually don't do it. Right? So that's a mistake. Bit shifting an int by a value greater than 31 bits. Right? Generally what we see this is people take a bunch of ints and they're taking these all and they're shifting them by amounts varying from 0 up to 56 bits, and they're assembling the result into a long. But the problem is that since the initial value is a byte or an int, all the shifting is done in int. They combine all of them, and then after all the combination, they turn it into a long. Okay, here's something that seen. So we've got X. So hash code is something that returns a 32-bit signed int, right? And you know if you take a negative number mod positive value, you might get a negative number. So we take its absolute value, mod the table length, and use that index into the table array. Does anyone know what's wrong with this code? Right. So the problem is that math.absolute value is not guaranteed to return a non-negative value. Right? This seems confusing, but that is the way it is. What math.absolute value does is if you pass it in a negative value, it returns the negation of the argument. And the problem is that when you negate integer.min value, you get back integer.min value. Right? And so the absolute value of integer.min value is integer.min value, and thus this can be negative.
It seems like you're straying from your principle here that this could be negative, but in most cases it won't be. So are you really reporting something for this?
So in general, so once again, we carefully craft things. In general, if we just see absolute value mod something used as an array index, we won't warn about it, right? However, hash codes are something that is sort of like the general spec for hash code is that a hash code could be any arbitrary 32-bit value, right? I mean, sometimes people define classes where the hash code doesn't occupy the full space of 32-bit values, but generally hash codes can be an arbitrary value. And no, I mean, there are lots of cases where you use an integer in your program where you know that it can't actually use all 32-bit values. It may not be expressed in the logic of your program or in the documentation, but you know that it can actually be all possible values. A lot of times you have parameters and you can't, and it actually doesn't make sense to supply integer.min value. Right? Whereas something like a hash code, or we actually also see it where somebody invokes the random number generator and get a random 32-bit integer, and that one's defined that, yeah, this one could return integer.min value. Right? So basically, we only do this in cases where we have a value that we know basically should be uniformly distributed over the space of the full space of 32-bit integers. Yes?
So you talked at the beginning about looking at places like the daily WTF and such as that to get your kind of bestiary of bugs.
Right.
And I have to wonder, like, where did this come from, and how did you evaluate kind of where it was in that power law distribution of bugs? How did you just, see one case of this and think I could write a detector for
Well,
that?
actually, so the
And I don't mean that about this specific case. What is your process for evaluating?
So this one actually came up with, I mean, I knew this little feat, and this one came because I was working with Joshua Block to come up with a programming puzzler. And we actually came up with an example that involved, it turns out that in Java actually has a definition for how you take the hash code out of a string. And it turns out that when you take the string polygene lubricants and take its hash code, its integer.min value. And so we actually came up with this example where you would get this behavior and the program would behave totally in the way in which things think. But so sometimes they come up from thinking, oh, this is something where you might do. And the thing is, well, that doesn't qualify it for insertion. What you then do is you implement it and I run it against 20 million lines of code. And I see what do I get, right? And then you got to go through and you got to review. Okay, is this giving us good information, right? If it turns out that it's generating a lot of reports that when you look at them you say, yeah, that's not really a problem, then you say, okay, this doesn't qualify. It turns out that this, with some tuning, like I said, what are the places where if you supply something here, you're expecting it to be a uniformly distributed hash code, right? It was pretty good. So like I said, I mean, sometimes it does come up with the idea that, somebody notes this weird quirk of the language, and then you have to say, well, can we write something that effectively finds violations of it? Do people actually make it? I mean, sometimes Josh has some idea, or I have an idea, and it turns out, well, yeah, you couldn't make that mistake, but nobody does in practice. right? In which case you say, well, you know, and if nobody does, but on the other hand, you're also not turning up any false positives, and maybe you leave it in, although you don't feel good about having spent the time doing it. But, yeah, question?
Just say, for instance, for this this rule, and this is pretty good.
Mm-hmm.
What is pretty good? What is your signal to noise ratio that you tolerate, and how do you put that line down?
So for the category of correctness issues, my goal is that at least half the warnings are ones that when you show them to a developer, they say, oh, yeah, I really think we should fix that code, right? Some of the other ones stylistically, so I mean, one of the things you get to, and I'll get to this in a little bit, is that there's stuff that makes you think, oh, I want to go change that code even though that code's been in production for a year. Versus there's also the category that, well, if this is the first time you've written that line of code, right, and it hasn't yet been checked into the source code repository, I want to change it. But if it's been in production for a year, I'm not going to touch it. And so the other categories are generally, I'd want to change this before I commit it. But if it's committed and it's passing all the tests, maybe then I won't bother touching it. Okay. So a couple things. One of the things we found more than we expected is bad code that isn't a bug. Right? We find ugly, nasty code that can't cause your application to misbehave. Right? Cleaning it up is a good thing. It makes the code easier to understand and maintain. It's good to never put ugly code into your code base in the first place. But if ugly code is already in production, sometimes you just don't want to touch it. We found more cases like this than we expected. So here's a case where our static analysis detected that this line of code would be casting an object to a type it isn't and always throwing a class cast exception. But there's a documentation there that that is exactly what the developer intended. The developer intended that cast to throw a runtime exception. Why they did it that way as opposed to throwing illegal argument exception or whatever, I don't know. But it's what the developer intended. Here's a case where they're checking to see whether or not something is a plain ASCII character. Right? They're checking to see if the value in this array is less than 32 or greater than 128. The problem is B is an array of signed bytes. And so if the high bit is set, it's going to be negative. Right? And so this check will never be true. But if the high bit is set, it'll be caught by this test. And so even though this code is stupid, it does what the developer intended. Right? So the code is doing what the developer intended. It's ugly, it's bad, but why change it if it's in production? Sometimes we see that, okay, here's a place where expected member name is null. We have a try. If either of these types of exceptions occur, the value will be null when it's dereferenced down here. Right? But the user has developer has put in a comment that he believes that these exceptions are impossible. Right? Okay, well, how important is that to fix? Well, maybe we should put in assertions that it's impossible, but on the other hand, if it actually ever does occur, we'll get a null pointer exception. Hopefully, we'll get a trace from that. We'll figure out that our assumption was wrong. So here's some code where there was a test. If null is equal to element, complain. This was the code. This isn't an elision of the actual code. It was an if statement where the body of the if statement was the comment complain. And then we dereference element. Okay, well, what actually happens if element is null? We're going to throw a null pointer exception. Well, that's a form of complaining, right? How would you fix this code? Well, maybe we should fix it by throwing an illegal argument exception instead. Well, is that really much different than throwing a null pointer exception? Okay, so we found a lot of cases like this. So usability. One of the things actually I've been doing a lot of work on is how to make the tool work. Just finding issues is only a small part of this. I've learned this probably more from talking to people like John Pinkus, stuff that's been done at Microsoft than anything else. So you guys all know this stuff. You need to figure out how to make it part of your development process, tune the tools to what people are interested in. You need to have a workflow. How do issues get audited, right? How do you do collaborative auditing? So you can see which issues are new in the last commit build. One of the things we find is really useful when we talk to developers who are initially trying to use static analysis. So we say, okay, and they say, oh, we've got 5 million lines of code. I ran your tool. It produced 500 warnings. We can't deal with that. What do we do? Right? So, okay, here's the first thing. Baseline, right. All the issues that are currently being reported that are also reported in the version that made it through your Q&A process is in production. Okay, let's deprioritize those. Let's assume those are important. Let's start looking at the issues that you've introduced since the last release. Those are likely to be the more significant ones. And actually the best ones are to find the bugs that some developer just wrote the line of code and the change he made introduced a new warning. That's going to be the most productive warning for somebody to look at a static warning that's just been introduced before you've run any unit tests, before any human has done, before you've done a code review of the code. Those are the best ones to try to find. Right? So let's see some overall results. So for Sun's JDK, I forget how many million lines of code this is, but we found 179 correctness warnings, and we found at least 213 of those are serious issues that should be fixed. That corresponded to about 1 million lines of code, 1 million lines of non-commenting source statements. From Google's initial version with this, over a 6-month period, they found about 1,100 warnings. From their initial triage, they reported about 800 of those as bugs, and 518 were fixed in the code base. Sometimes they find bugs in code, and then like, well, who's in charge of that code? Are we still using that code? Right? The developer who wrote that code left the company. Nobody's really in charge of it, and so sometimes you file a bug report, and it just sort of nobody pays any attention to it. Is there a question?
Do you know how big those both code bases are?
So the Java code base is about 1 million lines of code, the JDK. Google code base, there's actually weird stuff about what I'm allowed to say and what I'm not allowed to say about the Google code base. They actually allow me, we actually have a paper where we break out, we found this many of this type of error, this many of this type of error. I can't tell you how many lines of code it is. But I can tell you that the defect density is not substantially different.
Wait a minute. I can take my math degree and
Okay, so since we started 10 minutes late, I'm going to push to go 5 or 10 minutes late, and hopefully that won't cause a problem. Yeah, question?
Do you have magic patterns for concurrency bugs?
We have some. The problem, so we try to find some concurrency bugs. The problem is that generally it's very hard to find concurrency intent. You know what classes are intended to be thread safe, which methods are designed to work this way. So we try to find some. It's probably one of the areas where either and there are a couple of patterns that are very effective. One of the things we actually look for is we look for whether or not a variable is consistently synchronized, right? If there's a variable and 9 out of 10 methods where you access this variable, you're holding a lock, but there's one method where you're not holding a lock. That's a suggestion that that's maybe a problem, but that's a pretty noisy one. It's a pretty noisy thing. There are a couple of cases where we do find things that are more specific. It's also sometimes hard with concurrency bugs to convince developers that they actually do need to change this. Right? It's like, oh, well, I've never seen that occur in practice. I mean, the nice thing about some of the more correctness ones is you say, if you ever execute this line of code, you'll throw an exception. Right? Well, that's easier to get developers' attention. Or if you say, well, according to the theory of how the Java memory model works, this code won't work. And I say, well, I've never seen it work wrong in practice. And say, well, wait till you get up to 64 processors. We try to find some stuff with concurrency, but I think to do really well with concurrency, I think you're going to need some combination of more sophisticated analysis, information from the user about what they mean. And actually, one of the other things that I'm very interested in is getting some sort of combining some dynamic tracing information. So just getting some dynamic tracing information, such as these objects, objects of this class were accessed by more than one thread, right? That would actually be a huge win in terms of focusing the static analysis for concurrency bugs on the places where you actually have objects that are shared by multiple threads. Actually, let me mention another thing. People keep on coming back to this, so let me. yes, people say that like the vector class in Java is supposed to be thread safe, right? But then people say, well, but what about the equals method or the add all method? And so if you pass a vector as an argument to another vector and say add all elements, and while you're invoking that method, you change the vector that was passed as an argument, you have a data race. And so there's something which is sort of implicit in many of the methods, is that when you have a thread safe object, if you pass a thread safe object as an argument to a function, you shouldn't be changing that object in any other thread. Because basically otherwise, if you have a method that takes two vectors and you try to get locks on both of them, well, then you're asking for deadlock, right? And so there are a lot of unwritten rules about under what circumstances do I, do things in an appropriate way. Okay. So, so a lot of these, there are various ways. And like sometimes we start with an idea, and we do, but a lot of them work best when inspired by real bugs. So many different sorts. One of the things I do is just go through Sun's JDK, and they say, okay, what bugs were fixed in this build? And I look through them and say, okay, could static analysis possibly find that? Right? Sometimes I find things. One of the things that's interesting is you see places where you go through the bug database and you look at bugs reported against the compiler or a library that were resolved as not a bug. This is a place where a user misunderstood how the language or a library was supposed to work. And a place where a user misunderstands how the language or library is supposed to work gives you a suggestion of a place, well, there might be more places where people have misunderstood this library. Your own mistakes. I've actually gotten very good at when I make a coding mistake, turning them into a bug pattern. And sometimes those find bug patterns in other people's. So the daily WTF has a subsection, the code snippet of the day. Interesting and usually incorrect code snippets taken from production code. So this was something from actually this about 2 years ago. And I'm not going to, since we're running a little bit late, I'm not going to try to walk you through all of this, but it's like really horrible code for many reasons. We're appending something to a string. We get an out of memory error. We continue this loop and we keep on trying to do it. And so this was reported. The reply from support was, we're unable to see any problems in the code. Please apply a test case. Problems, well, it casts an int to a character, which only handles ASCII, catches an out of memory error. But the big problem is that the character value will never be -1. And the problem is that, so inputstream.read, it's a weird method. It reads a byte, and it either returns a value from 0 to 255, which is a byte value, or it returns -1 to indicate end of file. And then the code casts that to a char, which is an unsigned type, right? So if you take -1 and cast it to a char, it's not -1 anymore. And then we check to see if the result's -1. And so when we reach end of file, we will in fact keep on appending a character to it and going back in this loop, catching an error, continuing. That's one of the places where we'll get an out of memory exception. And so we actually wrote up a bug pattern to look for this. And so we found one version of the JDK, Java Server Faces 2, various versions of Eclipse 5, Apache VZip Tool 2, Apache Struts Upload 2, Apache Elan 2. Here's some of the examples. It occurs, we read and we immediately cast it to a char. Once again, we get next character. And these methods, it's back to like C error exception values. This method either returns a non-negative value or it returns a negative value, which is an exception value. Well, for some reason, even though they had exceptions, they decided to do this a lot of the way for input streams in Java. And people make the same old mistake. This was actually a slightly different mistake where they do a read, and rather than doing a cast, they end it with OXFF. And that, once again, turns the -1 into something that's not a -1. Okay. So methods that return -1 for end of file can be tricky. Code is rarely tested for unexpected end of file. You may need to use a mock framework. And don't assume any mistake is so unique that no one else could have made it. Okay, so now I'd been on the road for about 3 weeks. So this week I had some downtime, caught up on some of the things, and somebody reported to FindBugs the X or X logic expression should cause a warning. And somebody said we had some kind of error where the author meant if width less than some value or height less than some value do something. but instead had if with less than some value or with less than some value. So we could try to determine whether or not a condition is repeated. It's hard if you try to do it exactly and try to identify successive conditional expressions guaranteed to compute the same result. Well, if you actually sort of look at that formally, well, that's a hard problem. But we don't have to do it accurately. We can fake it. We did in about 2 hours worth of work. So here's something in Sun's JDK. They're checking to see if a JPEG image is subsampled. And so they get the H sampling value and the V sampling value. And they go through this array. And for every element of the array, they check to see if the H sampling value is not equal to H sample 0, and if the H sample value is not equal to H sample 0. Right? Pretty clearly, this should have been checking V sampling factor and V sample 0. Right? There's nothing semantically wrong with this code. I mean, it's not accessing outside the arrays of the outside the bounds of the array or anything like that. It's just nonsensical. Right? Why would you do something like that? Here's an example from Eclipse. Assert is legal. Context assistant is an instance of iContext assistant extension 4, and it's an instance of context assistant extension 4. Right? It's repeated code. And you look at the documentation, and it says we should be checking that it implements extension 2 and 4. Right? And so this is something that if you come from it, well, what is formally wrong with this code? Well, there's nothing formally wrong with this code. It's valid. It doesn't violate any language semantics. It's just probably wrong. So we started looking at the request for hands on Tuesday, spent about 2 hours thinking about implementing the first version. And a lot of times what happens is you implement the first version, and you go run it against 10 million lines of code. And you say, oh, we're producing a lot of warnings in places where we shouldn't be producing warnings. Right? And you have to go back and tune it and say, well, in this case, we're reporting a warning. We don't want to report it. How do I handle that case? Spent about another 2 hours refining it. Found several dozen instances. About half of them just appear to be redundant. There was a cut and paste. They cut and pasted. They're checking the same thing twice. It would really require a domain expert to tell me whether or not this was clearly a mistake or if they meant to say test against two different things. But a number clearly caused misbehavior. Okay. Let me real quickly.
Can you say a bit more about your implementation? Like how long, what interface do you use to implement a new pattern?
Okay. So we analyze Java class files actually rather than source files. It turns out that it's fortunate for us that Java-C does almost no transformation to the code. So there's not really much information lost in looking at that. Some of the stuff is a very simple visitor pattern over the bytecode. We do have an intra-procedural analysis data flow framework for looking at various types of information. And a lot of it is, sometimes it's really very simple. So for example, the methods whose return values shouldn't be ignored, we look for a method call. If it's one of these methods, we look to see if the next instruction is pop.
You don't have a language to write this type of pattern?
No, we've thought about that, and we sort of figured, well, we don't want to limit what we can do, right? And the other thing is, it works for us, and it'd be nice, but we haven't done that. Okay, so just about out of time. Let me just breeze through a couple of quick questions. Is dealing with reports by a static analysis tool the most productive thing an overstressed and overworked developer can do? If not, you need to figure out how to make your static analysis tool better suited to their needs. Some stupid code doesn't matter, right? A lot of static analysis code is designed at finding stupid or wrong code. How do we identify the cases that cause the application to misbehave in a bad way? Or possibly you might be interested in those that it can actually cause it to misbehave, but this is confusing as hell, and if anybody has to maintain this code, it'll cause them to cause it problems. Managed languages often mean that runtime exceptions are not so bad. Let me just fix it. No, I don't search PowerPoint slides. Right. So it just aborts the current query. How can annotations help? Annotations can help a lot. Which parameters are allowed to be null, relations between parameters, type qualifiers. But applying them has to be an effective use of developer time. right? Annotations to fully verify full functional correctness is useful only in certain specialized circumstances. Almost done. What aren't we looking for? So what types of coding mistakes matter and could easily be found with static analysis if we only thought to look for them, right? Encourage people to think about setting up a process by which when somebody fixes a bug or something, they just have like a little checkbox saying, you know, I think a smart static analysis tool could find this. And just start collecting those, right? You need to make something, because it's going to be developers. You need to get developers to start flagging what are the mistakes that might potentially be done. And to some extent, you know, yeah, you could, let's come up with a language for developers to write them. But the first thing is start collecting the examples and get as many developers as possible to start collecting those. Actually, another thing you can do is you can look at your change history and find all the places where there was a change to the code base that was marked as a bug fix and it was a one-line change. Anytime you see a one-line bug fix, and it's not a change to the documentation, the odds are probably pretty decent, and we've done this in some cases, that that's a change that might possibly could be found with static analysis. If they changed 500 lines of code, static analysis is not likely to do it. But it was a one-line change of code, maybe. What would actually help developers quickly produce reliable code? So I've been looking at the static analysis problem, but maybe this isn't the big problem. Maybe there are other things we could be looking at. They're much more important. I hope to get some ideas over the next year. Probably won't be anything I'm working on now. One thing I'm very interested in is how much of FindBugs could be ported to FXCOP. Last time I checked, FXCOP didn't report infinite recursive loops, obvious null pointer exceptions, many of the other things that we do. I'd love to know how many infinite recursive loops occur in C#. There are reasons it occurs more frequently in Java than in C or C++, like decorator patterns are a place where it often occurs. I'd love to find out how many, if infinite recursive loops also occur in C#. And if anybody would like to work with this. And I'm done and out of time, and the survey is being passed out, so we'll take questions. Yes?
So in all this, have you found anything? I mean, it's all been about, you know, simple patterns that you've been able to form. These bugs really do make a difference. That's great. That's one side. On the side of the static analysis, have you learned anything like, you know, certain analyses are just too slow, or you really needed to improve this? Has any impact on the static analysis itself? Has that all been completely just?
Well, so in particular, one of the places where we actually, you know, and we do a lot of continual refinement of this. Our null pointer analysis went through two phases. First thing we looked for is we just did a forward propagation, and we looked for a place where we see a dereference, and we're guaranteed that at this point that the value is null. Or actually, as far as seeing if there's an incoming edge to a dereference where the value is guaranteed to be null. And then we went to this sort of two-phase thing where we did the backwards propagation forward, and that about doubled the number of null pointer dereferences we were able to find. So that's a place where we've made a change, did some other things, but you know, it's not really been a research project about static analysis techniques, so yeah.
Can the user write his own pattern?
Yes, so the user can write their own patterns. You know, like I said, it's not a special language. You just write it as Java code. We've got a whole plugin architecture. So people have written their own plugin, so you can package your own plugin with your own rules, your own descriptions, drop it into a directory, and then FindBugs will load it.
And also, I think you can also turn on and off some patterns.
And you can turn on and off particular rules and things like that. Yeah.
What lessons have you learned for language design? What could languages do for these things that would prevent this error?
Well, you'll learn lots of little things. I'm not sure if you fix them, if that would actually make things a lot better, or if the errors would just skirt to somewhere else. I mean, so some of them are like silly things. So for example, in Java, one of the mistakes we find is when you write a method that's supposed to override a method in a superclass, but you get the capitalization of the name wrong. Right? And so in Java, capitalization is significant. So if you have a method which is identical to a method in a superclass, except the name is capitalized different, those are completely different methods. Right?
So say override.
Yeah, well, and so actually, one of the things we generally recommend is to use the @override in Java to say you mark which methods are supposed to annotate things. Having to put something in, I think in C#, you have to explicitly say that this method override 7 superclasses. Probably not a bad idea. So there's some stuff, I'm not sure. I mean, certainly when you look at a lot of the little stuff, it's not clear how many of those could be done. And certainly like, and I guess, I mean, like null pointer bugs, it's certainly one of the most numerous things we encounter. Having part of your type system as to whether or not something would be null, it would probably be the biggest thing that could get rid of a bunch of them. A lot of other ones, I don't know. And we can talk more about that. Not a whole lot of wisdom I can give in a real quick summary.
You mentioned generics, for example. Another one would be having an eval keyword to make a function, a return, something that returns something, ignore the return value on modulo 3. Or you had integer range problems. So for example, if there were unbounded integers in the language, I mean, but those things come to mind as...
Yeah, I mean, like I said, there are various things you could do. But on the other hand, if it's the sort of thing that you can find with static analysis, then maybe changing the language to get rid of that isn't the most important thing you could do. Maybe there are other problems that are more important that you can do by changing the language, like better ways to express parallelism or things like that, as really where the creative energy. I mean, if static, I mean, like I said, static analysis is very effective at finding when you've defined a method that's identical to a method in superclass except the capitalization is different. So maybe fixing that in the language just isn't that important, because we can find that with static analysis. And maybe what you should really be doing is thinking about what are the things that we can't easily find with static analysis, the place where the real problem is understanding developer intent and trying to figure out what's a better way to get developer intent expressed into the program in a way that either mandates the requirements or that static analysis can use to help understand and find errors in the language, in the program. Yeah?
So many of the patterns are actually cheap to check.
Yeah.
And so they should ideally be part of the compiler.
Yes, okay. So should this be part of the compiler? So actually, let me, runtime. Checking Sun's JDK about a million lines of code takes about 10 minutes. Okay, so pretty quick. One of the reasons to not put stuff into the compiler is that if you really only want the compiler giving you warnings that people are going to fix or put annotations. I mean, the thing is that you want to have some people. If you get to a point where the compiler is generating 50 warnings every time you compile your code, you've got a problem, right? Because people stop paying attention. If suddenly you get 51 errors, people are going to ignore it. And the problem is compilers generally don't have it's hard to get integrated into the compiler something that says, well, how do I mark which of these warnings have been reviewed and expected? You can do some of that with source code annotations. But one of the problems, for example, with source code annotations is that if you have people who are working on two different branches of the code, right, well, you're not sharing that information, right? And so basically, you need, if it's going to be in the compiler, you need to figure out how you're going to deal with false positives. Are we going to just depend upon putting annotations in the code to say, I expect this error, I've reviewed it and it's okay? Or for a lot of people, they don't want to just do annotations in the source code. They want to have a database for each issue where they do things. And that's one of the things that we're moving to on FindBugs. A lot of the static analysis tools are designed to store all the history of who has commented on this warning in a central database. Yeah.
You have your correctness attribute.
Right.
You have a class of bugs that you are sort of guaranteed to be bad as opposed to, you said before, 50% get right.
The question is, what is guaranteed to be bad? I mean, sometimes we find errors, like, okay, a statement that if ever executed will throw a runtime exception, or a method that if ever executed will throw a runtime exception. That's pretty bad. But sometimes somebody wrote that method because they were implementing an interface and had to implement 12 methods. And they just never call that method, right? So, you know, it's really hard to, you know, it's easy to get to 100% this code is bad. It's hard to get to 100% I want to change this code even if it's in production for 2 years.
Right, well, I'm thinking of what we've built into a compiler. For example, you know, you could say if this is guaranteed to throw an exception, but it's not a not yet implemented exception. Or I'm just, you know, because one of the ways of annotating code is to placate fx cop, which is change your code so that it does the correct thing, but it doesn't trigger a false positive, as opposed to annotate it. And sometimes the result is the code becomes a lot clearer.
Well, so here's the thing, is that the thing of having the compiler generate warnings, and you fix it by going in and you put in the annotations in the source code. That works reasonably well with new code. But you add this new warning to the compiler, and you run it against your old code base of 10 million lines of code, and you get 100 warnings, right? You don't want to go in and have to put in the annotations in that code base, right? And so, yeah, I mean, there are some things that, and maybe you do it with a more finicky thing, but this issue of how do you mark which issues, how do you do the things like baselining and so forth is one of the other things we talk about. How do you identify which are the issues that are new since the last release? And I think all of that needs to be part of how do you report warnings and how do people deal with them. Yeah?
Just to follow up on a little bit more of that.
Yeah.
The correctness of the compiler in terms of code generation presents a monstrous barrier to actually getting any kind of checking for other errors actually into the compiler.
Yeah.
The reality of getting the compiler changed because of the focus on correctness of code gen.
Right, so you don't want to be fiddling with any of the algorithms just because it would make it easier to do a static analysis.
The static analysis nuts who want to do static analysis don't have a lot of pushback to the core compiler.
Right, well,
and it's nice to have our own toys that we can play with.
Right. I mean, it's really, what tool it's a part of really doesn't matter. It's really a question of when you do a build, does the static analysis software look at the code? And you can do that regardless of where it is. And then the question is well, what sort of filters do you have? And maybe it would be nice to say that if you've got a new static analysis warning, somebody has to look at it before we do a commit or something like that. But I think we're probably greatly exceeded my time. And rather than more people continuing to sneak out of the back of the room, why don't we bring the talk to an official close, and I'll be happy to continue this conversation until somebody else comes to kick us out of the room.
Okay.
Okay?
Let's thank Bill.